On behalf of 24HourAnswers.com, I welcome you to today's lesson. In this video, we're going to look at two examples of evaluating limits, and it's going to involve us factoring first and then trying to plug our number in. And this first example here, if we try to plug in -6, the limit as x approaches -6 of this rational function, if you plug -6 into the denominator, you get 0. So that does not mean the limit does not exist. You need to try and factor and see if you can eliminate that piece that makes the denominator equal to 0. In this case, let's go ahead and do that. So we have the limit as x approaches -6, factoring our numerator, two numbers that multiply to give us 54 and add to give us 15. 9 times 6 gives you 54, 9 plus 6 gives you 15. So therefore we can factor this to be x plus 9 and an x plus 6. That's our numerator factored. And now notice we can cancel out the x plus 6 up top with the x plus 6 at the bottom. Now we want to evaluate the following limit. The limit as x approaches -6 of x plus 9. And now we can substitute the -6 in. Therefore we have -6 plus 9 is equal to 3. Now, this rational function is not going to be defined at the point -6, 3. We're actually going to have what's called a removable discontinuity or a hole in our graph. Let me show you that over in Desmos. So here we are in Desmos, and this is that function that I have graphed right here. It's the same one we just evaluated. And what I do want to show you is that it's really just a line, that red line there. And notice I have this green line and this red line. They're really the same thing with the exception of one thing. What I want you to notice is that the green line is what we had left over after we canceled out that common factor in the numerator and denominator. However, on the red line that we have here, as we get close to -6, notice this red dot here, our x value is -4.1 and our y value is 4.9. Notice as I let that x value get close to -6, notice the y value is getting lower and lower. And now our x value is around -5.8. Our y value is 3.2. Let's move a little bit more. And notice when I hit -6, we're getting ready to get an undefined. We have a hole in our graph. See how that red dot is now a hole? But notice as we were getting real close to it, that y value, that limit is getting close to 3. So even though the function's not defined right there, we are still getting a limit, and our limit's going to be 3. And the same thing applies from this side as well. As we get real close to -6, really close to -6, that x value, notice the y value still is getting really, really close to 3. So that's our first example there. And these are what we call removable discontinuities. More on that in a future video. So in this problem over here, let's try to plug in 3 into this rational function. I'm just going to go ahead and jump to the bottom. 3 squared is 9. 9 minus 5 times 3 is 15. Well, 9 minus 15 is -6. Plus 6, we get 0. So yet again, we have a 0 in our denominator. Well, let's try to factor. In this case, we need to factor the numerator and denominator. So therefore, up top, we have a difference of squares. That's going to be x plus 3 times x minus 3. And then in our denominator, we're looking for two numbers that multiply to give us 6 and add to give us a -5. Watch your signs here. A -2 times a -3 will give you that +6, and a -2 plus a -3 will give you that -5. So therefore we have x minus 2, that -2, and then x minus 3. So here we do have common factors in our numerator and denominator. Canceling those out, we are left with the limit as x approaches 3 of x plus 3 over x minus 2. And now we can evaluate this limit by plugging it in. So taking our 3 and plugging it in up top, we get 3 plus 3, that gives us 6. And then plugging the 3 in the bottom, 3 minus 2 gives us 1. Therefore, our limit here is going to be 6. Let's have a look at this graph over in Desmos as well. So this function here, x squared minus 9 over x squared minus 5x plus 6, we have this curve here. I'm just going to take this blue dot here, and I'm going to let x get close to 3 now, because our limit that we were just looking at was x approaching 3. Well, right now our x value is 6.12 and our y value is 2.214. So let's let x get close to 3. So right now our x value is 3.9-ish, our y value is 3.6, but notice as I let x get closer and closer and closer to 3, and right about here, oh, do you see that? 3. There it is. We have a hole in the graph yet again. But what I want you to notice is, even though we have a hole, the limit still exists because we are approaching. What y value are we getting close to? This y value right now is around 5.67. We're getting closer and closer to 3 for x. And notice that y value is getting closer and closer and closer to 6. Hence, that's why our limit does exist, even though our function is not defined right there. And again, the same thing applies on the left-hand side as well. So some things to bear in mind, we do have some new vocabulary here, removable discontinuities, that leads to holes. Again, more on that later, but the main goal here is for us to look at functions, in this case rational functions, where we get zeros in our denominator, but if we factor and cancel out a common factor, we can still find a limit to these particular problems. And that's it for this video. I hope it helped. Be sure to check out our YouTube channel for more videos. Links to our social media are in the description below.